who's currently at NASA Ames. And after this, I guess we're all off to dinner however we want. So hope everyone's had a good day. And soon we'll get to see something exciting.
Maybe. We'll see.
Oh, I'm sure.
No, it's already.
Click that little thing.
Maybe click this thing here. Just click this thing here.
That one. Just click
Oh,
that.
yeah, right that thing down there on that software.
That's what. Yeah, go ahead.
Easy to use.
I did.
Just click. Oh, you did already.
No, let's see. Oops.
There we go.
Oh, okay. There we go. Okay, and if you listen to the talk, you would have thought the talks today. You would have thought that Dan is solely concerned with sort of programming, and he's actually got a much broader view of the universe. He talks and reads about history and philosophy and so forth. And as a matter of fact, one of the first projects that Dan told me he had in mind when he met me was that he was going to do a book of poetry. Now, of course, these were Lisp poems. But he had the intention of doing a book of Lisp poems. And this was the canonical first example of what a Lisp poem would be. Are there people in the audience who haven't seen this one before? Okay, and among those, do you have any idea why this is interesting? Self-evaluate. Well, yes, it self-evaluates. It evaluates to this expression evaluates to itself, and then from there, I think Dan had the second example of a Lisp poem. Anybody know what this one does? It evaluates to its own reverse. And I think this one, I don't know if this is clearly not literally the thing, but the idea, I believe, is due to Doug Hofstadter, but at least that's what was explained to me at the time. Any guesses on this? Well, it's very strongly reversed. It even reverses words. And I figured I had to come up with one, so I racked my brain, and this is what I came up with. And this is interesting because, or maybe it's not interesting, but it's interesting because. What? Sort of. It evaluates to something which is not itself, which then evaluates back to the first thing. So, well, what else have I learned? I know that computer programming is an art. Don Knuth told me this. And software development is an art. Poetry is an art. And what's an art? Well, art originally meant skill at joining or fitting. And if you know anything these days about where most coding is just putting modules together with glue, you'll see that's very appropriate these days. Art is a system of principles and rules for attaining a desired end. The use of skill, which is aesthetically or intellectually pleasing. And, you know, of course, poetry, we ask about the aesthetics. I don't know if Dan has had any other Lisp poems in the ensuing 25 years. And, of course, very germane to computer kinds of thing, art is also used for necromancy in the Harry Potter black art sense. So that fits in very well. But what else what other things do people do? People do science. They distill knowledge into principles and laws. They do engineering, which is basically art with attention to economy. They do manufacturing, which is sort of repeated activity following a well-defined and low-skilled plan. They follow fashions. They select from equivalent choices. Okay, and many of these, art, science, engineering, show progress. Progress gets shaped by new technology. We invent casting, or we invent photography, or we invent computers, and new kinds of art appear. Shifting economic forces. The church stops paying for stuff, and the middle class, merchant class does, so the artists start producing more portraits and fewer things of God touching hands with the Pope or something to tell you how he's important. New understandings. We learn about perspective. It starts getting reflected in our art. And art also evolves in response to ideas of prior generations, especially so in the fine arts, where we're only doing this because it's the opposite of what the last guys did, but also so in computer science, because we do have to publish papers on something new. And if you look sort of like at fine arts, you see that things go through periods. You get primitive art, and the Greeks and Romans come along, and the Byzantines. And I may have the list wrong, just like the pictures are not in perfect order. But the world makes progress, and we get through neoclassicism with a very strong sense of trying to portray things the way they are, and then Impressionism, which is trying to convey emotions, and onto modern art and into a postmodern art. And as I mentioned, science and engineering are sort of unconditionally monotonic. Nobody in science says we should go back to Newtonian mechanics, or that non-Euclidean geometry shall be heresy again, or dolphins are fish. That's what Linnaeus told us. Fine arts revisit old themes, so the realism of the very strongly realistic paintings of the 19th century, sort of gets seen again in the photorealism of the late 60s. This contrasts with disciplines like, say, education and business management, where there are fashions. In the future, you may see the management practices of Attila the Hun, or the management practices of St. Francis of Assisi, and they have equal probability of being on the bestseller list a year in the future. Okay, but we do software, right? And one of the things about doing software, actually, is that it's so nice in all these dimensions, because it takes this great skill set that goes all the way from science and mathematics and testing things to engineering of trying to figure out how to make things work efficiently, onto artistic aesthetic measures, onto psychology. What's going to work for people's heads, both for the people's heads who are writing the thing and for the people's heads who are going to use the system, user interface issues. And for the people's heads who are writing things, actually it's sort of some of the fundamental discussion about everything we've said about programming languages here, because we know they're all Turing machines. You don't need scheme. You can just write with ones and zeros, as the last talk showed. So there's a whole lot of things a whole lot of ilities, a whole lot of things we're trying to get out of our software systems. There's an aesthetic of understandability. We care about how easy it was to write the stuff to begin with. In other circles besides this one, people care about how easy a system is to maintain or evolve. That involves doing things like comments. We care about how efficiently the code executes. We care about how reliable it might be. And actually, once you get out of Scheme, sometimes things don't work the way you expect them to. This internet stuff has introduced this entire security issue. When you start using your art of skill in joining, you have to put things together in interoperable ways, and the list goes on. That was the off my top of my head list. So strongly in this, there's sort of a Sapir-Whorf hypothesis as applied to software development. Sapir-Whorf suggested that people's language shaped the way they think about the world. It's a good debatable proposition, but it's great for putting up on slides. So the belief here is the programming language you use affects the way you think about building the software, which is, for example, for us here, we couldn't understand half of the Gang of Four book, because the Gang of Four book is the patterns book, because half of the patterns book is just how to get out of the dumb things that C++ makes you do. We don't have to think about that at all. You want to go through a set, you go through a set. It's not a big deal. Now, programming languages are an intellectual progression. They started, just like the art guys are an intellectual progression of the physicists. Programming is specification. I heard this most nicely expressed by Mitch. I don't know if it's original with Mitch, but he's got some slides somewhere that sort of say it very concisely. The earliest programming languages were concerned with efficient realism. They had made it hard to, at that point, it was hard to sort of get the computer to do anything. So you took a highly structured problem like, say, computing a math function, and you had this slow machine with relatively little memory, and you were concerned with could you get it to work at all. And the programming was very linear. The things you said in your program tended to correspond one-to-one with what happened in the execution, and the programming was very planar. You could sort of trace through what might happen. We come to a go-to statement, and there are an if statement with 3 go-to choices, and we can see where the 3 places are going to execute next are. And programming progressed, and it went from a Fortran-y pure functionality to notions of structured programming and abstract data types. And for the majority of the programming universe, I would say we're probably in an object-oriented space, so much that sort of even Dan and Matthias have noticed object-oriented programming. There are, of course, have been other notice, that's all. Matthias gave a nice talk in Oslo last summer, which was basically, yo, you object guys, and if you just understood functional programming, all your problems would go away.
Which isn't true.
What?
I didn't say that.
Half of your problems would go away, something like that. And of course there are a bunch of other distractions, but they won't fit into the rest of this talk perfectly, so just remember I know these things exist. Okay? But, modern art reached its limits, and Newtonian physics reached its limits. And a good question for us to ask is what are the limits of object orientation and how are we going to get past them? What's going to be the post-object programming of the universe? So for example, in object systems, all meaning is wrapped up in the code. Whatever the system does is what the code says it does, and that's it. And if there's something else you want to do, like say verify the system or test it or maintain it, there's nothing there that's going to particularly tell you about what's going on. There might be some comments or some UML documentation, but I think those may fit into the obfuscation or the lack of information space. Unitary modularization. This is Harold Osher's notion of the tyranny of the dominant decomposition. Object-oriented systems make you say, well, first thing you do is tell me what your objects are, and now make everything else you do fit into those objects. So there's something you care about somewhere else that isn't about those objectnesses. Remember to do it in all your objects. That's where the information will get spread out. The world isn't made up of discrete, unconnected objects. It's more continuous than that. There are, if you look at a database and you look at a set of database views, there's a lot there that doesn't match neatly to objects. If you go to the real world, there are mass terms. There's the ocean, and then here's a little piece of ocean for you. If you look at actually trying to do modeling of things, here, let me give you a car, and the car has some wheels. Well, the car is an object, and the car has some wheels, and the wheels are objects. But they're not all that independent. Like, the wheels in the car are if you want to know where the wheels are, where the car is a strong hint. With the following has, particularly with all the verification talk, the net effect of all this is that people do not write correct code in object systems, and we keep acting like we think they can. That's going to be a problem. Objects are set up for a model of call response. I'm going to have this thing with a particularly well-defined behavior. I ask it a question, it gives me back the answer, and that's the end of it. But people have richer qualities of interactions. Maybe our post-object programming will see something about that. These are general-purpose programming languages, but we all know from Dan's work with graph languages that some things are better said than something that knows what the hell you're talking about. So what are some of the ways we might get out of these limitations? All the meaning is wrapped up in the code. We might be finding ourselves with richer uses of annotations, in some sense semantically not so much executable as meaningful annotations, not UML or comments. So when it comes time to verify or test the system, there's something there that will help. Unitary modularization, one of the things that we've been working in lately is aspect-oriented programming, and I'll give a few slides on this subject. The universe isn't made of discrete connected objects, so we may find constructs to describe composites, collections, masses, things that will let you maintain relationships rather than writing all the code to maintain the relationship. Things that deal with the persistence of things rather than telling you that was somebody else's problem. We may see more of a notion of the merger of the database view and search with our programming languages. And these are my guesses. You get to add your own. Inherent inability to create and maintain correct code. Where I think we may be heading is more towards autonomic computing. Autonomic computing basically works on the theory that what you're writing is not going to work, so tell me what to do about it then. And there are nice things that can happen from this, even with systems that learn about what kinds of failures you've got. Will we see an end of tyranny of call response? Well, actually, we see a lot of it now. There's a lot of event-based computing because every time I press a key on this thing, an event goes off through the GUI system to tell it that the next slide is supposed to show up. But in general, models like publish and subscribe are a lot easier to say some things and a lot harder to say others. We may see things where there are conversational or protocol kinds of things built into the language so that you don't have to transfer an entirely large amount of state over to somebody to get some information out of them if you're telling them a lot of stuff they don't need. Or, if you ask a question, the response may come back, why do you want to know? I can phrase my answer in that respect. And I can remember that you're talking to me, so when you come back a while later, I'll know what your state was. We may see more context-aware systems. This is a bit of a buzzword in the ubiquitous pervasive computing universe, which is when I wander around with my PDA, then I should know what printers are around and what coffee shops are in the neighborhood, etc. And I once thought this was just one more parameter, but I'm coming to the belief that this is more complicated than that. There was in some sense a fad for a while in domain-specific languages and extensible syntax. I don't know whether we'll see this come back or not. It's clearly the case to me that I'd rather use Yak to write a parser than C or Java, but whether that's sufficiently generalizable, I don't know. I don't know where those ideas will mix in. Okay, so let me go back to the one that I promised a few more slides on in our postmodern programming. Programmers care about a lot of things when they code. Remember all those ilities. And current programming technology tends to demand a dominant decomposition. So you break your world up into your objects, and then make sure when you code your objects that you take care of all these concerns. So if we care about security when we access the database, or make sure that all your database access code does the right security things. And there's actually even a harder thing we ask about our programmers, which is we want them to worry about all these concerns, even the ones that don't exist yet. So if you're building this thing in a pre-internet era for a machine that just sort of runs in one place by itself, well, 15 years from now, somebody will come along and say, yes, but what are you doing for security? I see there's no security here for the network hookup. What network hookup? It wasn't there when I did it. And also knowing you can do a lot to encapsulate concerns in conventional languages. You can make subprograms, you can make inheritance, and conventional languages basically force programmers into knowing how to get these other kinds of concerns to do their thing. So I may not have to be the security expert who can write the encryption code, but I do have to know to call the encryption code and what places in my code it needs to be called. So what are things that are concerns? Lots and lots of things are concerns. Concerns exist at both the requirements and the design level. So some things are concerns that you can talk to your customer and the customer knows that you want reliability and that you have to do something about it. And some things you can talk to the customer and the customer had no clue whatsoever that this was an issue. Like, I want to cache information that's come across the net so the world will be more efficient. Good engineering. The emerging interesting technology on this is aspect-oriented programming. It allows the separate specification of concerns, some description of how the concerns interact with each other and the overall system, some kind of annotation, and then some kind of tool that will make it all work together. There are varieties of tools. There are tools that do compilation ahead of time. There are things that work by changing the interpreter to a meta interpreter. So in a funny kind of sense, this is dumbed down meta systems, or maybe sped up meta systems. You can do things that take the object code and go play with it, or stick hooks in the object code, and these are the various kinds of technologies emerging for this. Now, so if you're developing an ALP language, you want to talk about what kinds of places other concerns might interact, and how you might want to make them interact. And there are some other issues about ordering and visibility and conflict resolution. Okay, so Dan and I did a paper once that has gotten some fair amount of play in the ALP universe, which sort of asked the question, well, why is this different from everything else we've been doing already? And the answer we came up with was, this is a technology that lets you write statements that talk about the program or part of the program as a whole, and the program you're talking about doesn't particularly have to know that what you're saying is about to be applied to it. So the first of these notions is quantification. I want to be able to make some statement generally, like whenever you call the database, you need to run the security code, and there's nothing in the database call in your code, obliviousness, that says, yo, check the security property. Okay, so at NASA we've been doing working on a research regime, and actually Mitch and Matthias's student Dave Herman was working on us this summer, their previous student Jeff Palm, where we're trying to describe a language of events and actions on those events, determine how each event can be reflected or made visible in the source code, its shadow, and creating a system that transforms programmers with respect to these events. So this is the Trinity system. Sometimes the things that you want to talk about, there's a strong correspondence between this. So the Trinity system talked about, in some sense, what can you say about a program? And we identified three kinds of things we might want to say. I should back to the top of my slide before I do the middle one here. One of which is you can look at the program as a syntactic object and talk about it, like I'd like to have all the uses of the variable x. You can talk about things that are the result of doing static semantic compiler analysis. I want to talk about all the things that are the x declared right here, or all of the statements that might follow the execution of this one. And you can talk about the things that might happen dynamically in the course of a program execution. So let me know when that particular object gets called, or let me know when the thread swaps, or that's a hard one, by the way, or let me know when the garbage collector runs, which is an even harder one. And sometimes there's a strong correspondence among these structures, and sometimes there isn't. So if you want to know when a variable x was referenced syntactically, you can pretty much find the places in the code that say x. And semantically, you can go through and find the places in the code that say x, or you can stick something on all those references to x and find it. But if you want to know, for example, when the garbage collector runs, there won't be much in the program at all to help you. And so the shadow of a quantification is those places in the code that might be affected by something you've asked to have done. So this gets us an architectural view. We're going to take something like source Java code and take a description of some event actions and transform the Java code so as to produce stuff that does what the original does, plus all these other things that you said you wanted to have done. And this is work in progress. So we're going to transform programs based on pattern action rules. When the pattern of a quantification is seen, we're going to transform the program. The rules become, in some sense, like database queries. Transformation can be structural. It can change the original program, or it can be behavioral. It can perform some action before, after, around, or instead of an original target. We note that making structural changes on events don't make sense, doesn't make a whole lot of sense. Whenever there's a garbage collection, I'd like to declare another variable x. And there are a bunch of nice things you can do if we actually ever get this all to work. One of them dear to Bill's heart is that Bill's system for introducing traces into the universe becomes the kind of thing you can do to a program and it sort of, you know, here make these transformations rather than I'm going to build a system to do it. And similar to tracing, you can do profiling. How often does each statement execute? More generally monitoring, so if we want that autonomic computing system to respond to the innards of our black boxes, we can stick the right things there. What are some of the others? People have used AOP for security issues. We care some about debugging concurrent programs. I believe you can write garbage collection, or at least reference count garbage collectors as add-ons to your program in this. You might not think that matters, but there's a version of Java that doesn't have garbage collection for the particularly small machines. You can use this kind of tool to do refactoring. You can use this kind of tool to introduce persistence. User interface was a cute one. Somebody said to me, and the big problem we have is that we can't get people to put undos in their system as they build user interface. I said, well, maybe we can do that one too. Find every place where something gets changed and retain the state. And that's all I had to say, so I may even be done on time. Who did this get borrowed from? Mitch?
Any questions?
I take issue with something you said early on, and ask how you address it, which is that whereas in fashions things come and go, but in science and engineering it's monotonic, and yet we have really important examples of things being lost, of knowledge that's lost for 1,000 years, or just information of how to do things, but really science engineering things that disappear for a while and have to be rediscovered, recreated. I wonder how that fits into this.
Well, this is a broad comic. You notice, by the way, for example, we started with the first one was pictures from Minoan civilization at about 1500, and they were drawing cartoons, and they're, you know, we end up in modern art, and they're drawing cartoons. This one, by the way, is called Syntax and Semantics. The name of the painting. And everything I've said has been done with a very, very broad brush. So we clearly do lose things. Biz school is probably not, and biz school and education are probably not nearly as bad as I portrayed them, but at least it's good for a laugh with this group. We do lose technologies, though I suspect the rate at which we lose technologies will decline dramatically the more and more literate and the more computer storage we get. What? Will accelerate losing stuff or accelerate?
Yes, you bet. Try to find a URL that's 5 years old.
No, but he's asking something more broad, which is, I want to know how to mummify bodies. And the Egyptians figured it out, but I can't.
Well, yes, you can. But you do it pretty well.
Well, it's his thing, and that was the best example I could come up with off the top of my head. What's a good example?
Damascus steel.
What?
Damascus steel. People did not know how to make it for maybe over 1,000 years. Sure. It was known during the Crusades, and then it was lost. And it was rediscovered in the late 70s.
Okay. However, nowadays I suspect somebody. What?
They lost zero.
You want to point out the more discord we get, the more space there is to lose good ideas. And the massive garbage that will be.
And now I can actually summarize what my talk was about at eCoop. It was not about functional programming is good. It was, I just wish the object-oriented community remembered what they knew 20 years ago.
And so I guess the connection to your talk is, do you see part of the future of where programming languages are going as recovering some things that may have lost from the past?
I think that yes, there are clearly ideas that have been in the past, but will show up again. The aspect stuff, for example, has a whole lot to do with multiple inheritance. It has a whole lot to do with mix-ins. It has a whole lot to do with meta-interpreters. That stuff, you know, some fraction of this is fashion, and you're being schemers, you clearly understand that some fraction of it all is fashion, and some fraction of it is economics in funny ways that we don't broadly appreciate.
Going back to poetry, what's the saddest program you've ever seen?
We don't want to embarrass Chip Ricky.
Microsoft Windows?
You haven't seen that.
But,
I don't believe you've seen that.
no, it depends on the definition of scene. Sad, you mean the ones that I've written, huh?
Sad. Something sad. Something, you know, happy programs, that sad programs.
Status lines are what
Some of the Little Whisper stuff after I started dieting.
Just a comment about forgotten technologies in the discovery. Security. A lot of the security, especially multi-level and strong security, and the approach that the secure system has to be proven secure, has been lost in the 70s. And, for example, Multics had secure kernel, and VMS had actually operating system that really used several security level of the process. And Multics spent a lot of time making security right, and it was the only one system that had 8.1 rating in origin. And then all it's lost. And actually there was a project, for example, doing multi-level security, right? I mean, really hard multi-level security. And that requires formal proof. And it was in the 70s, there was a formal proof by actually ACL2 prover. And they built a system, it's like at the end of 70s. And they already got the login prompts. And then the government pulled the money, pulled the fundings, and everything disintegrated because they said, well, I mean, who needs the security? We just put several boxes, I mean, independently, everything, I mean, solve the problem.
Yeah,
Now, I mean, many years later, then we have so many different classifications, then it turns out if you put all this in different boxes, then you run out of space. I mean, physical, literally. And so we now go back and we go examine all the things, how they did the security. Now, try to discover all the principles in the secure system. Try to retrofit, everything that was in Multics and the Unix, which was never designed with any security in mind.
And this is true. And by the way, the people giving you the requirements to explain, they also want you to run on Microsoft Windows on the net with the system that you're doing.
Oh, yes.
And it can't get in anybody's way too much either. You don't want it to get in the way of our getting the work done.
Any other comments? Okay, thank you, Bob.
Sure. Thank you.